Okay. Well, thank you again. Thank you for giving the floor. This time I am going to go deeply into, well, more or less deeply, into the assessment method 3 developed under ePANACEA methodology. It's based on auto-calibration of white box building energy models for EPCs. Well, at the very beginning of the project, we made some research about the set of standards, of the EPB standards, and the current status of the EPC schemes in the 5 pilot countries that are involved in the project. And we defined this scheme as a global approach to cover different scenarios of data availability and to cover also different objectives to be met by the energy assessment itself. This first approach is included in the report on the use of innovative certification scheme and its implementation, available in the project Zenodo community. Okay? This report suggests an optional benchmarking based on the future availability of actual energy use databases of the building stock, but also the general scheme proposes a complete workflow to meet several objectives at the same time. The workflow shows the inverse modeling from the data collection through the calibration procedure to the limitation of uncertainty of some parameters. As you can see, this scheme is a little bit complex, so we try to simplify. Then we simplify and translated this previous scheme into this concept, the so-called EPC cycle, where we start from a very simple first model and follow all these steps by using the functionalities already implemented on the CEPAP tool developed by the project. So first, we start with the development of this first building energy model with dedicated tools. Then we go to the definition and adjustment of actual peak loads and operational schedules according to available data, monitoring data, and other information. Then we proceed with the auto-calibration step with the use of parametric analysis and optimization algorithms. Then we use this parametric analysis to select the most suitable model for using it as a calibrated model. After we correct this calibrated model into the standard operational conditions. And finally, we proceed with the assessment of the proposal for energy efficiency measures based on the actual use. So it means based on the calibrated model via a cost-optimal approach. So we are going to go deeply to each of these slides, okay? Then the CEPAP tool. The CEPAP tool has been developed as a local tool based on OpenStudio. Okay, OpenStudio is a cross-platform collection of software, as you probably know. So this cross-platform allows to support building energy modeling using Energy Plus, a simulation engine. OpenStudio is an open source project to facilitate community development, extension, and adoption by the private sector. So it includes graphical interfaces and a software development kit, very useful for our purpose in this project. Then this cross-platform integrates several open source applications that have been adapted to meet the objectives of the ePANACEA project. Specifically, the CEPAP tool installation package includes the OpenStudio SketchUp plugin, the OpenStudio application, the parametric analysis tool, and the OpenStudio server. All of these tools or software application, well, we have incorporated new functionalities to all of these applications to easily introduce characteristics of the building, such as the envelope and system, perform simulation, conduct the parametric analysis, and the automatic calibration of the model. Well, here some examples. There is the plugin of the CEPAP tool over the SketchUp application. Related to the second step, is the step to get a pre-calibrated model. We use the actual operational conditions. In this case, taking advantage of the ICTs and the accessibility of actual data, for instance, from utility and weather station data servers, preprocessing data scripts had been developed to allow detailed modeling of actual user behavior for the dynamic simulation. This step enables also the decomposition of electricity consumption by service, as well as the corresponding hourly fractional schedule associated with actual consumption. Also, automatic processing of the actual weather data has also been implemented to develop compatible format files for specific calibration years. Then, this is the calibration workflow we use in this assessment method proposed by the ePANACEA methodology. Some steps are performed locally, while others, mainly related to the iterative calibration procedures, are carried out through an optimization algorithm and are executed at the server level on the cloud. Sorry, this step. We use a genetic algorithm that uses evolutionary theory to approximate the objective function that has proved a good behavior for this type of assessment. In this case, the optimization function is defined for minimizing the value of errors, ideally 0 or close to 0. As an acceptance criteria, to consider that we have obtained a good calibrated model, we use the criteria from the ASRAE guideline 14 that establishes a maximum of, taking into account monthly data, establish a maximum of a value error of 5% for the normalized mean bias error and a maximum of 15% for the coefficient of variation of the root mean square errors for all energy carriers present in the building. So we follow this criteria in our automatic process. So in order to follow the previous scheme for conduct the auto-calibration, the ePANACEA calibration template is used in the parametric analysis tool, where a list of open studio measures for the variation of the calibration variables has been implemented by default. Here, this is an example of one of these measures. This template also incorporates the default values for the optimization algorithm, the objective function, and the range of variation of the calibration variables associated. In this case, we have used a normal distribution, okay? More or less like this. We have introduced default values, but the technician may adjust this range of variation according to the source of the data if necessary, okay? If the uncertainty of the data are low, we can reduce this rate of variation to reduce the scope of the assessment. Well, then we just need to access to the calculation server and proceed to launch the analysis. After approximately 30 minutes, 1 hour, depending on the model and the initial configuration of the server, we will have access to the results. So through the console, we go to the View Analysis tab, and although at the OpenStudio server console we find several functionalities to explore the results, this one is the most useful to allow dynamic filtering and select the most appropriate model for consider it as our calibrated model. In this case, we can filter this and select the most suitable one. The vertical axis represents the variation of the values for each of the calibration variables, and the last four are the errors for the electricity and natural gas. Sorry. As I said, with the two types of error, normalized mean bias error and coefficient of variation of the room squared mean errors. When we select our final calibrated model, we have all the results associated to this model. As you can see, the results are quite good in this example and meet the requirements of the ASRAE guideline 14 with an error values very close to 0. So we can find the decomposition per energy fuel, per energy service, per service, and per month, or of course, from a dynamic simulation, you can also report hourly results. Well, a step that we have incorporated in our methodology is the automatic correction to standard operational conditions. This step is automatic from the CEPAP tool implemented, the plugin implemented in SketchUp. So in this case, this functionality corrects our calibrated model by a weather data file, loads, schedules, set points, and so on, and get automatically the results for these standard conditions. So, it's what you mentioned about the procedure for develop this correction to standard conditions to use this model for EPC or regulatory purpose. This is a suggestion to do that. Well, finally, as an additional functionality, we are exploring at the moment the possibility to implement an automatic cost-optimal assessment in the same way that we have implemented the auto-calibration. This would allow to conduct this type of assessment by non-experts about parametric assessment. Because we think that although originally the cost-optimal methodology is defined for reference buildings, optimal results can differ from one building to another, due to different characteristics, orientation, design, and so on. So in this case, we use the life cycle cost and the source energy as the parameters for optimization via multi-objective function, and representing these values in the chart you can see in the bottom of the slide, if we represent the Pareto from of this cloud of data points, we can identify the best option, the options related to cost-optimal solution or nearly zero energy building, or indeed the positive energy building. Here we found an important handicap, that is the parameterization of investment costs, which is challenging indeed because they are not linear many times. So we are studying this at the moment. As an example for the comparison for this case study, in this case is an office building located in Spain with about 5,000 square meters. So if we comparing the results for this case, we see significant differences, up to 65% in some services, which is normal, due to the difference in loads, schedules, set point, and weather data used in one model or another. In this case, the indicator in terms of primary energy for both the sum of EPB and non-EPB services will have a value of almost half of the actual use. So, as a conclusion, this implies that an important distortion in terms of informing users about the energy savings derived from the proposed energy efficiency measures based on one model or another. So, as a conclusion, extract from this part of the project, focus on the assessment method 3, I think we can say that the development of accurate models that reduce the current performance gap between theoretical and actual consumption is possible with cost-effective procedures. For instance, 2-3 working days for complex buildings. With the appropriate tools, it is possible and feasible to extrapolate the methodology based on auto-calibrated white box models from the scientific to the commercial environments. Multi-objective optimization based on genetic algorithms plus parametric analysis in the cloud allows to reduce the computational cost of the calibration process. Also, we think that the automation of the workflow based on available computational tools will reduce the need for professional training in terms of cost and time. Another conclusion is that if the estimation of energy savings resulting from the implementation of energy efficiency measures is not based on the actual use of the building, so it means based on the calibrated model, we cannot guarantee the accuracy of these calculations. The use of calibrated models within EPC schemes would reduce the uncertainty of some parameters. Also, use for the EPC standard, indeed, no? Such as the global thermal envelope transmittance or the outdoor air renovation inside the building. So when we fix the values for these calibration variables, we use these values also in our standard model. According to this research and also in collaboration with the workshops on end-user perceptions and needs, we think that end users show a higher level of engagement with energy efficiency when the EPC information is based on their occupant behavior patterns. It means on actual energy use, on the calibrated model. And they perceive this information as helpful in making decisions about investments. Regarding the next steps and future research lines, we are right now finishing the conduction of the 15 case studies in the 5 pilot countries to confirm the initial findings. It's still ongoing but well advanced. Automated cost optimal assessment through a multi-objective optimization via the parametric analysis tool to achieve the nearly zero energy standard or the positive energy building standard is still ongoing, is related to the last slide before. And also we are exploring the possibility of the integration of this methodology into national simplified EPC schemes as a future development. No? We are thinking specifically in developments in the context of Spain, where we are involved in the tools and software that are officially recognized to provide the EPCs. I also invite you to check the project YouTube channel and watch the video tutorial related to this assessment because it has been carried out almost in real time. And the video tutorial duration is about 1 hour and a half, but including the explanation of the context, the case study, and so on. So you can have an idea about the time required for the whole procedure. And we think that is well optimized for the complexity of the workflow itself. So thank you so much for your attention.